My name is Shiyi Luo. My research is about the efficient deep neural network comparison. How about finding the balance between making these models smarter and keeping their accuracy up? Do we need to compress machine learning models? As we all know, to pursue better performance, the models are becoming deeper and deeper. So the number of parameters greatly increases, occupying more memory. We can see here, most of these models have hundreds of parameters leading to high growth. This makes them very unfriendly for deployment on devices like mobile phones, Raspberry Pi, and PGA. In this work, I use Tensor-Train Decomposition method to compress models. Tensor-Train Decomposition is a kind of low-rank decomposition which leverages the matrix multiplication properties, decomposing a large tensor into the product of several smaller tensor cores, thereby reducing the size of the entire model. Here's an example to see how TT decomposition impacts the number of parameters. Typically, the formula of an original tensor is the first one. After tensor-train decomposition, the formula will be the second one. We switch from multiplication to addition, which reduces the total number of parameters greatly. For example, we have a tensor A sized 3 by 4 by 5, and we set the rank to 2. Using our formula, we can calculate the number of parameters, 32 versus 60. Then, from the formula of parameter calculation, we see that the rank is important in determining how many parameters are after tensor-train decomposition. The lower the rank, the fewer parameters. However, the rank value has a big impact on everything from model's accuracy to its computational complexity and how well it converges, which could lead to either overfitting and underfitting. So I designed the budget-aware automatic framework. Let's break down the approach a bit more. First of all, I've chosen to use a compact TT convolutional layer because it has stronger comparison capabilities. Then I use the method called weight imprinting to evaluate the importance of each layer in the CNN. Finally, I've designed an automatic rank determination algorithm. This figure displays the pipeline within a CNN for each layer. Start by applying TT decomposition on the weight. Then right after each TT layer, hook up a proxy classifier. The classifier uses the weight imprinting technique to evaluate the importance of each layer. From this, we can get a TTL score for each layer. Using these TTL scores, the designed rank selection algorithm figures out the best rank for each layer. Once we got all the ranks set, we are able to fine-tune the entire model to optimize performance. That's the whole process of my approach. Let's keep going. The next part is the experimental part. I primarily use the CIFAR10 and CIFAR100 datasets. I utilize the models from the ResNet series, including ResNet 20, ResNet 32. Given the low-shot nature of my method, 50% of the dataset were sampled as a more time-saving way. The figure shows the rank search process. The blue bar represents our full dataset method, while the gray bar represents the sampled version. The graph shows the changes in TTL scores for each layer during the first 10 epochs of training. We can see that the TTL scores for each layer start to stabilize as training goes on. Both of these two methods are able to quickly estimate the layer importance. And then regarding to the experimental result, the figure on the left shows the final related rank distribution. By multiplying these values with a scaling factor, we can determine the final ranks. This step allows us to adjust the ranks based on specific needs, ensuring budget-aware optimization. In the table on the right, Gamma is the scaling factor. We did the comparison among the original model without model comparison, TT decomposition method with fixed rank, and our automatic rank decision methods. With 2 times comparison, the accuracy of my methods only dropped a little bit from the original. Even when we push it to 4 times and 6 times comparison, the accuracy stays within acceptable limits. This shows that my method can really decrease the model size while keeping performance strong.